It's a great pleasure to introduce our speaker of today's SMC colloquium, Alessio Figali from ETH Zurich. And before I hand over the floor, I do the needless action to introduce him a little bit to you. So Figali obtained his PhD in 2007 from the universities of Pisa and Paris, I guess already.
Lyon.
Lyon, that was still Lyon, also at the end. Okay, sorry. At Lyon, under the supervision of Luigi Ambrosio and Cédric Villani. And he worked at the time on optimal transport and action minimizing measures. He directly got CNS position, like Chargé de Recherche is like a permanent position in France that awarded to a few people in the country which have the best research results during the thesis, basically, and he could directly obtain one of those. Became a professor, like junior professor at the École Polytechnique in Paris in 2008, and the next year obtained an associate professorship at the University of Austin in Texas, where he stayed for quite a few years until 2016, when he became a professor at ETH Zurich. In the meantime, he collected a number of awards, of which I selected a few. I think one clear sign was the MS Award, the MS Prize in 2012. He was an EICM speaker in Seoul in 2014 and received the Fields Medal, as we all know, in 2018 for its contribution to optimal transport and its application to partial differential equations, metric geometry, and probability theory. And today, we hear him as a world expert speaking on the topic of free boundary regularity for the obstacle problem. Please take it away.
Okay, thank you very much. Do you hear me well? Yeah, good. Okay. So thanks for the introduction. Thanks for inviting me here in Stockholm. It's been a few years since last time I visited here. Today I would like to talk about a different topic from optimal transport, which is the obstacle problem. And actually, there are many experts now in the room because there is also a workshop currently taking place in Mitterglechter. But for those experts, I'm sorry, this won't be super exciting, especially the word first part. But I want to give it very self-contained. So let me start to talk about the obstacle problem. So the obstacle problem, before putting the obstacle, let me start for some motivation. So let's say that I have some metal wire, and it's good that I call it fence. So you have a wire that you model, let's say, with as the graph of a function. So I have my domain here, omega, and I have a function f that represent my wire. So I have a function f from boundary omega into R, and then the graph of f represents my metal wire. And to this metal wire, I want to attach an elastic membrane. Okay? So we'll have an elastic membrane here attached to this wire, which represents by the graph of some function u. So I will have now u from omega into R, and then the graph of u is an elastic membrane that I will attach to this wire. And essentially I want to understand, given the wire, so given f, I want to understand the shape of this elastic membrane. So the problem, let's say A, the basic one, would be, okay, what is how do you find the function u whose graph represents the elastic membrane attached to f? You have to minimize some energy, and the energy you minimize, so there are many very complicated models in nonlinear elasticity, but the simplest could be do linear elasticity. So if you go to linear elasticity, you just put the gradient of u squared, let's say I like to divide by 2 over omega, and you minimize these over all functions that coincide with f of the boundary. So this is linear elastic energy. Okay. It's easy to prove under nice assumptions on F and the domain that minimizers exist. And then what you do? So let's say that you use a minimizer. And then what you say, you want to find the optimality condition. So you say, okay, if you use a minimizer, I'm gonna compare you with another competitor. So you fix some function phi, let's say smooth, see infinity and compactly supported in omega. And then you say that by minimality, the derivative with respect to epsilon, at epsilon equals 0 of the energy, so the integral of grad u plus epsilon grad phi over 2, this should be 0, because this is the energy of u plus epsilon phi, and a minimizer means that is a critical point also. And then you compute this. This is the same as grad u times grad phi, and then you integrate by parts, but phi is compactly supported, so there is no boundary term, and then you get the Laplacian of u times phi. From which you deduce, since phi is arbitrary, this has to be 0 for every phi, that the Laplacian of u is identically 0. So harmonic functions can be modeled, can be found in this way by minimizing elastic division energy. Then you could make things slightly more physical, and then you say, okay, well, let's complicate a bit the model. So I still minimize the same energy a priori, grad u square over 2, but then I say, okay, wait, there is, in physical world, for instance, there is gravity. So because of gravity, there is here some gravitational force acting, right? So the gravity vector. So let's say that my omega lives in a Rn, and then this is the En plus 1 direction. So I'm in a Rn plus 1. So there is gravitation force, and then I have to consider my wire. My membrane will feel the gravitational force. So I will have G times U. So U is the height, and then the higher the height, the more gravitational energy I pay. And okay, for simplicity, I'm gonna put G equal 1. We are mathematicians and we like to normalize masses. So G is 1. This is the energy. You do the same computation as before, you prove that the minimizer exists, you compute the variation, then you get Laplacian of U 1 because of this extra term. Okay. So far so good, but there is no obstacle. Now let's put an obstacle. What does it mean? It means that I have my wire again, so let me draw it again. But now, under the wire, there is a plane. So this is x, let's say n plus 1 equals 0. And now, remember there is the gravity. So the gravity will make my elastic membrane bend. So while maybe without gravity, this was my elastic membrane, with gravity, perhaps my elastic membrane is what like this, will be more something like this. So the shape of U will be something like this. So the plus 1 forces the function to look a bit more convex. And now I could do the same. So I still minimize my energy. So the energy will still be as before, minimize U on the boundary equal F integral over omega of grad U square over 2 plus U. But now I tell you that this plane acts as an obstacle, which means that my elastic wire, my membrane cannot pass under this plane. So it's like my membrane here, and I hold it, but this table is here, and my elastic membrane cannot cross. So it means that somehow, somewhere, it will touch the obstacle. So here I have an extra constraint, which is U greater or equal than 0. So my function is not allowed to go negative because of the plane of this table. Okay. So this is now my new problem, and this is the obstacle problem. So the classical obstacle problem, there are many different formulations. You can generalize it in many ways, but let's say in its simplest standard form, you can put it in this way. And now you want to write the equation, the same as you did there. Then you got Laplacian 0 or 1, let's say, and then what happens here? So here you have your minimizer, U, which represents this elastic membrane that touches the obstacle. So here where it touches, U is identically 0. And then where it doesn't touch, in this region, this is the same as this equation. Where you don't touch is like if there was no plane below it. And then here you will have Laplacian equal 1. Because it's like in this equation. And then, okay, you have to be careful perhaps to understand really what happens here. There is some work to be done, but I can tell you as a fact that in fact nothing bad happens here. So either you solve the Laplacian equal 1 or you are 0. But when you are 0, if you think this region is nice, then if your function is 0, the Laplacian as well is 0. And therefore, so the Laplacian is 0 here and is 1 there. So the equation becomes Laplacian of u equal characteristic function of u positive, u non-negative. Where I remind you that the characteristic function of a set at a point x is 1 if x is in A, 0 if x is not A. So this is just a compact way to write what I did. Okay. So this is the PDE associated to the obstacle. And then, I mean, I'm a PDE person, and then a PDE person looks at this and says, what can I say about you? You know, if you have taken some PDE class, you know that if u is harmonic, u is analytic. Essentially, harmonic functions are the best. So no matter what boundary data you put, f could be anything, but once you go inside and you are inside omega, the Laplacian, knowing that the Laplacian is 0 or 1, it doesn't matter, is a constant, tells you that it is analytic, so u is super nice. Now things are a bit more complicated. I'm telling you that the Laplacian is a non-smooth function of u itself, because a function which jumps between 0 and 1, depending on whether u is positive or not, or positive or 0. So the question that you ask when you see this is question 1, how smooth is u? And then question 2, can I say something about this contact region? So this is the free boundary. How smooth is the boundary of the region u positive? So this boundary. We call it free boundary because it's the boundary of a set which is not prescribed by us, it's part of the problem itself. So a priori it's free to do what you want. And we want to tell him, okay, you can do almost what you want because we can put theorems that tell you that you cannot do something else. So what about this question? So answer to 1 is actually very easy. And answer to 1 is actually very easy. Well, not very easy, but let's say it's not. It will be like now 1 second. The focus of this talk will be on the question 2. So answer to 1, essentially, this has been already answered in the 60s. There have been many different proofs from Frese and then the original proof fairly later, but there were a lot of contributions that tells you that u is as smooth as the PDE allows you to do. So what do you know here? Look at this. So Laplacian of u is bounded from this equation. Bounded by 1, because it's 0, 0, 1. And what is the Laplacian? Laplacian is the trace of the action of u. It's the sum of the eigenvalues of the action. So it's the trace. And the Laplacian of u is bounded, but is not continuous, because it jumps from 0 to 1. Okay, so what you can prove is that from Laplacian bounded, you can prove that the function is, in this setting, u is C11, that is, the action of u is bounded. So the function u is differentiable one time, and then the derivative is continuously differentiable, so it's C1, and then the derivative is differentiable again, but the second derivative is not continuous, it's only bounded. So it has discontinuities. Okay? So it's twice differential with bounded but not continuous second derivatives. And you see that this is optimal because the second derivative cannot be continuous, because if this was continuous, this would be continuous. because it's the trace of the dash. So this is optimal. The proof is not trivial. I'm not telling you that this is something trivial. I'm just saying that this is something now more than 50 years old, and so kind of classical, not really classical. For sure, much easier than proving whatever I will tell you from now on this one. So answer to now the focus will be answering question 2. So when we work in PDEs, there are many theories in PDE. So there are like, okay, I want to understand the theory of regularity, perhaps for very nice equation, like the Laplacian, or equations which are close to Laplacian, so with nice coefficients. So perhaps the Laplacian is not exactly Laplacian, the coefficients which are still nice. And you can prove what is called, there is a theory which is called Schauer theory. It's the theory of regularity for PDEs which are nice. And then there is a theory of PDEs when the PDEs are rough. The coefficients are the coefficients of the PDE are very rough. This would be like what is called the Georgi-Nash-Moser theory. So there are theories for 2 words. And usually Schauer is much easier, and then the Georgi-Nash-Moser is much more complicated. So here, what would be the analog? The analog is, I would say, is a theorem by Kinderle and Nirenberg in 77. What they proved is the following. I will draw a picture to explain. So let's assume that I have a ball of a certain radius BR, and inside the ball, I have a surface that separates u equals 0 from u positive. Okay, so I have a nice surface separating the two regions. And I'm going to assume that this surface here, sigma, the free boundary, is C1 in BR. Okay? So the free boundary here is a nice upper surface that separates the two regions. So I have zeros everywhere on one side, and I have 0 positive on the other side, and I know that is C1. Then sigma is infinity. So once you have a bit of regularity, you have a nice geometric configuration where you know that you have the free boundary separating nicely zeros from positive in a C1 function that it has to be super. Okay? Which would be like saying, okay, I start from a harmonic function, it's like at the beginning perhaps it's not very regular, but then it becomes super regular. This is like the Schauer theory in some sense. Of course, this is a conditional result. It's telling you if you can find this, then you get this. But then, how can I find this? I mean, how can I guarantee that these assumptions are satisfied? So this is when I would say Caffarelli came into play. So Caffarelli in 77, he proved, I would say, probably the most fundamental result in this setting, which was really the beginning of a huge amount of work, which is the following theorem. So the theorem of Caffarelli was that the free boundary of U positive is the union of 2 parts. Regular part, disjoint, and union singular part, this is a disjoint union. So it consists of 2 pieces. What is regular? Regular are points as in Kinderle-Nirenberg. So I have points where I can find around each point in the regular set are points such that in around each of them I can find a small ball where I have this configuration. Okay? And then the rest is singular. Okay, what can you say about singular points? And this is he proved that the following. So a point is singular if the following is true. So let's say 0 in the boundary, 0 singular. What does it mean? It means the following: that for every radius r, there exists a vector ER on the sphere. So it's there is a fixed dimension and in a Sn, such that so this is 0 on the free boundary. And I will have a direction ER such that I take the plane orthogonal to ER, so this is ER dot x equals 0. and my free boundary is trapped in a small neighborhood of this plane. So let me use the color, the blue. The region, something like this. The region u equals 0, it's like this. This should be. So here I have a ball of radius r, and here I have a small neighborhood which is a little of r, so something infinitesimal with respect to r, and the region u equals 0 is here, which means that here u is positive and here u is positive. So essentially, free boundary points are the following. Either you look super nice, or around this point, I can find, for each ball, I can find a plane, a hyperplane, such that my free boundary is super close to that, and the function is positive outside. So let me give you an example that hopefully will clarify this. So example, n equal to, I do this. So this set that I'm drawing in black is u equals 0, and here u is positive outside. This is the possible contact set, and then all points here, excluding the tip that I'm drawing in red, is regular. Because you see around each of these points, I can find a small ball where I have u0 one side and positive on the other. And then, of course, the ball depends on the point. And then here I have this segment, which is made of singular points. Okay, so singular point has these very thin points. Whether there is, I don't have a nice zero. I don't have a nice separation between 0 and positive. The positive region is dominated. Okay, and this is, I would say, a very illuminating example because it shows something actually, in some sense, very bad. Is that regular is here is the union of two curves, and singular here is a segment, which shows that regular and singular may have the same size. You know, perhaps in many problem geometric there is this idea that you have singular points and regular points, and usually the regular points are the most points, and then singular points are lower dimensional in some sense. Here is not the case. The singular set, the regular set are as big. I mean, they have the same size. They're both one-dimensional objects. Okay? Which, you know, you would say is not that bad. It's not super exciting. Okay, so this is about the structure, and now we start to focus on this singular set. So the philosophy, once you see a Caffarelli paper, is that, okay, great. Thanks to Caffarelli and Tivernier, the regular points are essentially fully understood by themselves, in the sense that they are made of a super nice infinity, effective and analytic hypersurface. So this, like here, this is a super nice curve. The singular set, okay, this example looks nice, it's a segment, but okay, it's not so obvious that this should always be the case. So what can we say about the singular set? So now the next goal is understand sing. So this is our new guy. More precisely, I will ask 3 questions. So I will do question 1. So question 1 is, can we understand how smooth is the singular set. You see here, so this is a picture, but so far all I know is something like super weak. I only know that if I fix a point in the singular set, my singular set is close to a plane in some qualitative sense, but it's not super smart. Second question. So reg and sing can be same size. This is what I just showed you. Is this common? In the sense, okay, you just picked an example, but how artificial is your example? If I give you a different boundary condition, so this solution comes from some boundary condition because U is equal to some metal wire on the boundary, right? So the problem is you start from some boundary condition, you minimize, you find U. Okay, perhaps you can build U which looks like this, but if you perturb a bit the boundary conditions, can you still see something like this, or this is very rare, a phenomenon like this? So is this common or not? Third question is what we call blow-up analysis. So how to study free boundary problems in general. So to study the free boundary, we like, this is Caffarelli did it already in 77, to do blocks. What does it mean? It means the following. I start from my solution, let's say, and I have some contact set. It goes here, and there are. This is my solution. Let's say that my solution is defined. This solution is defined in some ball B1. Let's say this is the origin. Okay? So I have my solution. Maybe I should have done B1, not possibly. So my domain omega is B1, let's say, for a moment. So my solution is defined in B1, I have my contact set, whatever, doesn't matter. And then my free boundary. And then my goal is to understand the free boundary. So what I do to understand the free boundary is to zoom. Is to say I'm going to take a very, very small radius, little r. I'm going to take the ball of radius r around that point, and I'm going to zoom it to make it of size 1. So blow-up analysis means that from there, I'm going to go to the following picture instead. So BR becomes B1. My free boundary will grow, so it will be something now more looking like this, perhaps. The origin is the origin, and then it keeps going. So you see what looked very small now is size B. So what do you do here in this? So here you're doing a change of variable. Here you're doing a change of variable, which is U R of x will be U defined at the point Rx, and you have to divide by R squared. Why you do this? Because in this way, the Laplacian of UR, when you take the Laplacian, you take two derivatives, so when you differentiate twice, there is an R squared coming out that simplifies. And this becomes characteristic of UR positive. Okay? Now, this function is defined in B1, but now, you see, this was B1 and this is BR. Now BR has become B1, so B1 has become B1 over R. So UR is defined from B1 over R into R. So it's defined a very, very large ball. And then what you're going to do, you're going to let R tend to 0. So you zoom in, you keep zooming in. Your functions UR will convert to some function U0. And my U0 now will be a function on the whole space, which will satisfy Laplacian of U0 equal characteristic of U0 positive, but everywhere in a range. Okay, so all possible limits of blowups, and this you can do it in many ways. You can do it by fixing the point. You could even do blowups. Even so, you can even do these along sequences. So you will take different sequences of radii, but you could do it even changing the free boundary point. So you fix a point, you zoom by r, you fix another point, you zoom by another r, and so on. And you keep rescaling, and you take any possible limit. And then you will end up with a global solution. So this is a global solution of the obstacle problem. So if you can classify all global solutions, then you get something interesting, because you can say, so if I know how this looks like, I know essentially how this almost looks like before passing to the limit. So it will tell me something about this region, because this region in the limit has to converge. So this region, which is the zero set of this, in the limit should converge to the zero set of this. So you see that analyzing the free boundary through this graph analysis, in the end, gives you nice information if you can characterize all global solutions. Okay, so these are 3 questions I wanted to raise. And now let's try to give some answers to 1, 2, and 3. Any questions? Okay. Okay, let's go with 1. Can we understand osmosis singular? Yes, so I would say the first important result on this direction is again Caffarelli, 98. So he proved something better than what I will state now, but for the sake of simplicity, I would like, because I want also to spend a bit more time on the next questions, I will focus on this now, on a simpler version. So in 98, he proved that the singular set is contained in a C1 surface. So he had some kind of regularity results that tell you that there exists some C1 hypersurface. So if you have dimension n, the surface has dimension n minus 1. So I should say hypersurface. That covers the singular set. Okay, it means that the singular set a priori cannot do whatever it wants. Notice that. So, okay, for the expert, you will not like this statement because it's not really what he proved. Caffarelli proved that. He proved that there is really a stratification of the singular set in surfaces of different dimensions. But let's just focus on this simple statement. So you have an upper surface that covers singular set. How optimal is this? So you see, for the regular points, I told you something much better. I told you that a regular point, if you fix a regular point in a neighborhood, you look like this. So the free boundary is really made of a super nice hypersurface in a neighborhood. Here I'm just saying that not the singular set is a C1 hypersurface, but it's contained. So how optimal is this inclusion? How optimal is this inclusion? Okay, let me try to build for you this example. So you take a line, and then you start again, that probably you know already, that you take, let's say this is 0, 1, you take 1/3 and 2/3, and then you draw a super smooth curve on the top, and then you say u is 0 here. Then you do 1, 9, 2, 9. Take a super smooth curve here and here, and you say u is 0 here, and you do the same on the other side. And then you keep doing 1/3, 1/3, and so on. As in your construction that you already know. Now, all these points, except the last point here and here, all these points are regular. Okay, so and then you keep doing, and then you build your solution here. So u will be positive here, and it's gonna be 0 here in all these regions. Okay? This is all regions what you see. And then it's positive there, and it has to satisfy the PDE. You can prove that such a U exists. Not really with one, but okay, there are some details. But believe me now, I don't want to enter into the legalities. I can enter later if you have questions. But let's say the point is that in the end, what do you find? You find a solution which has these as contact set. And what are the singular points? The singular points are those left outside. So in this picture, singular points is the Cantor 1/3 set. So whatever is left, which is the Cantor set, is the set of singular points of your free body. And the complement are all regular points. So you see that the singular points are actually very ugly, are a Cantor set inside a line. So they are not a smooth surface in any sense, but they are contained in a smooth surface. They are contained in a set. It's the smoothest you can do. Right? So singular points can be better. Okay? They don't have really structure. And we, in the last years, there has been a lot of work to try to understand how optimal is this statement, especially at the level of inclusion. So recent improvements. So first, myself and Joaquim Serra, in 2019, we proved that the singular set is contained in a C11 surface, again the surface, up to codimension 3 to a codimension 3 set. So we started to stratify the singular points even more. Said, okay, the singular points are not the same, all the same. You can analyze them further and understand really how they behave at very small scale. And there are points which are nicer than others. There are some which, they behave much better and they can be covered with smoother surfaces. And then there are other points that we call the anomalous points, which are lower codimension. They don't exist in dimension 2. They start to exist only for dimension 3 and higher. And these singular points are ugly. I mean, there is nothing you can do. But they're smaller. You see, they start to be smaller. While the singular set, so singular set, this is an n-1 dimensional set, and these points are n-3 dimensional. So they are codimension 2. So you start to see a bit of structure. We went on with this analysis with Joaquim Serra and Xavi Rossoton in 21, and then this has been also refined later by Franceschini and Zaton, PhD students of ours, in 21. And they proved that singular set in reality is contained a infinity of surfaces. Up to anomalous points, so up to this codimension 2. Well, no, here you have to go to codimension 2. Yeah, because there are discrete points. So there is a stratification. So C11 is actually optimal if you want codimension 3. If you want, you can go to infinity, but then you have some points that you need to remove already in codimension. But the point is that the singular set is. So this looks strange as a statement at this level, but the reality is that there is a very precise full stratification. That tells you the singular points is a union of pieces, and then there are pieces which are all kind of rather not explicitly stratified, but you know exactly how points behave in each piece. That's right, and you can say, oh, these points behave like a infinity part, these points behave something different, blah blah blah, and then there are some points which are super ugly. We cannot say too much, but they are of codimension 3. Stuff like that. So this was essentially a big piece of work that we did in the last years. And the reason why I wanted to state also this is because this is interesting and useful if you want to study question 2. So perhaps I will erase this part. I will keep, well, no, I can erase the first part, which is and we can start to discuss a bit of question 2. So question 2 is about the size of regular and singular points. So I told you that in explicit examples, and we have an example up there on the other black whiteboard, the example of the segment in between the two drops. So you can have examples where singular set and regular set have the same size. Okay? Let's see. Okay. Now, in 1974, Scheffer made the following conjecture. He said, generically, sing equal n. So he conjectured that, okay, the singular set can exist, here examples, but if you perturb a bit your problem, perhaps the boundary condition, then in fact you shouldn't see any singular point. So that's a very rare phenomenon. It was very vague in the statement, so he didn't explain what Fourier generically means. Okay? There have been a result on this question in dimension 2. So there was this conjecture true for n equal to this was done at the beginning of the 2000s. Okay. But this was done in 2003 by Monod. But let me explain you what we did, and this way I can also explain you what I mean by generically. So the way we did generically, we took then our way, because anyhow Scheffer didn't tell us, which was the following. So we have our boundary data, right? F. And for each F we have our solution U that will touch our plane somewhere. So we are going to take, to make things generic, we need to be able to move our boundary data. So we're going to take, so let ft, t in -1, 1, let's say, be a one parameter family of functions defined on the boundary omega. So we take a one parameter family of boundary condition, and we want them to generate enough variations. And for simplicity and convenience, we're going to assume them to be mono. So let dpf be strictly positive. So things move. Okay, so I start with my boundary data in some way. And for each f, I solve the obstacle problem for each f of t. So I consider Laplacian ut, the characteristic of ut positive, ut non-negative, and ut on the boundary omega equal. This is my problem. So now I have a one parameter family of obstacle problems that are all ordered because the ft are ordered. So if t is less than s, you can prove that ut is less or equal than us. If you read the boundary data, the corresponding membrane will be higher than if the boundary data are lower. And then you start to work with this one parameter family. You start to analyze all the singular sets, the singular set for all this family of solutions. So you have this one parameter family, a countable family, and you start to understand how free boundaries talk to each other. Because the free boundary will talk to each other. Because every time one single function does something, so let's say that I know that my function has a certain Taylor expansion, for instance, then all functions which are above that Taylor expansion. So there is an information that propagates up and down, and so on. So there is a way to make them talk. And then we analyzed, we use this method to kind of make the singular set, the singular points talk to each other, and we drew the following theorem. So this is the paper I mentioned in 21 with Serra and Rossoton. We proved that for almost every t, hn minus 4 of the singular set of ut, sigma t, is 0. So if you take your boundary data and you perturb a bit, for almost every t, just with respect to the back measure, so this is the back measure on the minus 1, if you do, so essentially for a set of full measure you have this. The singular set has 0 n minus 4 dimensional measure, which means in particular, if n is less or equal than 4, then sim t is empty. So generically, the singular set is empty in dimension 2, 3, and 4. And if you are in higher dimension, we cannot say that it's empty, but we can say at least that there's codimension 4 in the whole space. So at least it's very small compared to the whole free boundary. So if you just look at the free boundary, you will not see much of singular points. Okay? So this was really a combination of the answering 1 and 2. Now what about 3? Probably, yeah, I did the blow up here. Yeah, let me erase this. About question 3, this is actually a funny question because it's actually related to a theorem which has more than 300 years. Okay. Okay, so about 3, what do I have? I have a function u from Rn into R, where Laplacian of u is the characteristic of u positive, and okay, so this is a global function. Okay, define rho density to be characteristic of u positive. So this is a density which is 0 in the contact set and 1 outside. Then what is u? I will be a bit informal here because there are problems with diverging stuff at infinity. So, but if you think that, so let's say I have some contact set, I don't know what it is. Let's say I have a contact set somewhere. This is u equals 0, and here u is positive. Okay? And here I put constant density 1, okay, outside. Then Laplacian of u is equal to rho. So if you think of rho as either mass or electric charge, you can decide if you like gravitational or electromagnetic force. This is a density, let's say mass density, and then u is the gravitational potential generated by the density. Which means that, so u is the gravitational potential, so minus grad u is the force field, is the gravitational force generated by rho. Okay, you may have a bit of problems if you think that rho is plotted everywhere and you cannot do convolutions with cameras, but let me. So this can be made rigorous. Okay, and then what happens here in the contact set? Here u is 0. So if u is 0, grad u is 0. So what does it mean? That grad u is 0 means, so if u is a solution to the obstacle problem, then there is no gravity inside u equals 0. Okay? Which means that if you have a global solution to the obstacle problem, and you put a uniform mass distribution of psi, then this would generate no gravity inside the contact set. Okay? And then you can ask yourself, okay, how many shapes have this property? This becomes like a geometric question in geometric analysis, right? You have in your RN, you have a certain shape, you put constant density outside, and you ask how much, which shape are such that if you have uniform density outside, there is no gravity inside. So the first theorem that said something about this was 1678 by Newton, who proved U equals 0 equal a pole. So in the statement of Newton is a sphere. There is the spherical shell theorem of Newton that tells you that if you put a uniform density in a sphere, this creates no gravity inside. But then if you think that, you see, you have a sphere and you start to do the union of spheres, so you just take, you take spheres of radius r between 1 and infinity, this will give you the complement of a ball. So U is a ball, and so which means U greater than positive is the Rn on the. So Newton did it for the boundary of this set, which was the sphere. You can go from one to the other. There is no. So Newton proved that the balls are global solution to the absolute problem without formulating that way, of course, right? But they are equivalent problems. Of course, here there is a small catch, the non-negativity that I hide at the table here because there is no negativity here. But it's known by now that this is a consequence. So in fact, there is a full correspondence between these two points. So here I cheated because I didn't discuss this constraint, but it's not. So you can believe that in reality these are fully equivalent problems. Then around, I haven't checked the reference exactly, but around 1800, first Laplace in France and then Ivo in UK. So in the period there is a French version and a UK version. They say that the U equals 0 should be an ellipse. But we use E to denote an ellipse. So if you give any ellipse and you put constant density outside, this will create no gravity inside. Now, if you have ellipsoids, you can start to take limits of ellipsoids. So you can take, you fix the origin, let's say, and you take a family of ellipsoids center of the origin, which have the origin of the boundary. You take them larger and larger, and you take the limit, and in the limit you can generate any parabola. So by taking limits, U equals 0, it can be a paraboloid, or U equals 0 could be a paraboloid cross RK, or an ellipsoid cross RK. So you can always add trivial dimensions. You can always take a ball cross some k dimension. So you can always build extra dimension. But so this is the set. This is the situation. So essentially, in roughly 200 years ago, we knew that the family of global solutions include these, and these. Of course, you know, if you take paraboloids which are larger and larger and larger, in the limit you will get a half space. So paraboloid, which includes half spaces. Half space. Right? So if you take a paraboloid which infinite opening, that half space, and I implicitly say that this is a paraboloid. Okay, so this is the list we have, and then people started to wonder: is there something else? So the first result in the converse direction, trying to classify these global solutions, was given in 1931. So, so classification. So 1931 types. Oh, of course, all these things were done for n equal 3. I mean, Newton did n equal 3, Laplace never did n equal 3. You can show that it was in every dimension. So Dice in 1931 proved that, again, n equal 3 U equals 0 compact, so you have a bounded set, then U equals 0 is an ellipse. Okay. Then there was an important result in 81 by Sakai, which was n equal 2, and he proved that U equals 0 is either an ellipsoid or a paraboloid or an ellipsoid times a k. Well, in dimension 2 you cannot do much closer, so well, that's it. Well, in dimension 2 there is no product. It was so exact. And that's it. So Sakai proved that the list is already here in dimension 2. The proof uses complex variables, complex analysis. So, you know, in two-dimensional harmonic functions are related to homomorphic functions. And then you have a lot of tools. So the proof is really two-dimensional. Then in 1986, there were two papers. First, Di Benedetto, Friedman, and then Friedman, Sakai, and they proved that U equals 0 compact and greater or equal than 3, then U equals 0 is. So they classified in every dimension. So this, if you put these three things together, what do you know? You have the classification every time the compact set is compact. And in dimension 2, you know that there is nothing else. I don't know about the story, how people felt that way, but let's say, I think once you start to see this, you start to believe probably this is everything you can hope for. This was written explicitly the first time, I think, in 1992. Henrik Shagolian conjectured there is nothing else. So this list should be exhaustive in every dimension. Probably then Eric, I don't know, maybe you can comment later about how it came out, I don't know. But let's say, I think it's a very beautiful and natural conjecture that you can make. And of course the problem now is the compact case is understood, the problem is the non-compact. Essentially, I would say nothing happened in this direction for almost 30 years, until 2020. So 2020, Simone Berg, Eric Shagolian, and Georg Weiss, three of them are in this room now, proved that yes, if n is greater or equal than 6. So they could prove the conjecture, but only in high dimension. I don't have much time, but maybe I can say one word later about why this. And then finally, this year, Eberl, myself, and Georg, yes, if n is greater or equal than 3. Which finally closes the yeah, there is a difference. So there are situations where low dimension helps, but there are also situations where high dimension helps. And just to understand an example of why this helps, and then I will stop. If you give me a paraboloid, so I told you that there are problems of convergence at infinity there when you start to do, fundamental solutions. So how do you build the gravitational potential associated to a set? You convolve your charge with the fundamental solution of the Laplacian. Okay, so the way you build usually gravitational potential is to say I have a charge rho, and I convolve it with the fundamental solution. Okay, I will, instead of doing the charge for rho outside the set, I will put the charge inside. So you can ask, so fix a paraboloid P, and consider the characteristic of P, so the derivative function of P, convolved with the green function G, where Laplacian of G is equal to delta. What is this?
not non-empty in theory?
Oh yeah, of course. Well, let's say the empty paraboloid, the ellipsoid, let's say empty paraboloid, then it's okay. If it's an empty interior, then it means that there is no. This is 1, then Laplacian equal 1. So this should be an empty interior. If it has empty interior, then there is no constraint. You just solve the Laplacian equal 1 with no negativity, and then you can put this quadratic parabola. Fixed P, consider this. So what is the green function in I dimension? Is 1 over x to the n minus 2, up constants, the green function of the Laplacian. And then you ask yourself, okay, what is the convolution? And is the integral over a paraboloid, right? I have a paraboloid here. So this is, let's say, r n minus 1, and this is r. This is paraboloid. And you integrate the paraboloid 1 over x minus y to the n minus 2 dy. And this would be like your gravitational potential. So some, let's say, V generated by V. Okay, something like that. Now you can ask you can do a computation and check when does this integral converge. I mean, when I integrate something on the workplace. When is this integral converge if this is a paraboloid? So you take a paraboloid in this, you compute when this is convergent, this is finite, if and only if n is greater or equal than 6. So in I dimension, the decay of this helps much more. Again, when you integrate against a paraboloid. So that's okay. It's not the reason why they couldn't do it, let's say, but this is a reason why there is a high dimension helps. Okay, because you have nicer convergence estimates in high dimension than in low dimension. And in fact, I would say 6 and higher there was disadvantage. 4 and 5 looks more complicated, but still in this framework. And then 3 is really the difficult case of this problem. 3 is the most challenging. And I think I took all the time I had, so I will stop here.
Thank you very much for the wonderful talk. Let's ask for some questions or comments from the audience.
You should take the microphone, please, for the recording.
Well, thank you for your talk. Well, all these results that you showed somehow are very general. But like at the beginning, you start with a set omega with some boundary and some function on the omega. And I wonder if you know more about this boundary behavior and also the function f, what you can say about this similarity and of course all these results.
Yeah, so thanks for the question. So in some sense, okay, I've been a bit vague, but in some sense, implicitly in all my results, I made assumption. So implicit assumption. What I made was that f is strictly positive on boundary omega. Okay, which means that my wire doesn't touch the table; it's really lying above the table. Which means that the set u equals 0 is always compactly supported inside omega. Which means that once you are outside from omega, you see there is the contact set here somewhere, wherever it is, I don't care. Here is omega. And here Laplacian of u equal 1. So I have a layer between f and is which comes from the fact that u is super nice. And in that sense, no matter how ugly this can be, it doesn't matter anymore. Because you see, if you just artificially say, okay, I have my domain omega, let's say that f is only continuous, for instance, older, I don't know. I find a solution, but it's not so. Okay? But then, this is analytic, no matter what. Then you just replace, you can find omega prime in omega, which contains u equals 0. And then your u will be the solution of Laplacian u equal characteristic of u positive in omega prime, and u on the boundary omega prime is equal to u as a boundary condition, which now is analytic. And this I can take it as much as I want. So as long as I make this assumption, the boundary condition plays no role. If I relax and I put greater or equal, then it means that perhaps the free boundary could touch the real boundary, and then of course the boundary condition make a lot of importance, both the smoothness of F and the smoothness of the boundary domain. But that's a different question that I haven't at all addressed today. Actually, all our work, everything I stated, all these theorems are really for the interior analysis. There is another analysis that you can do at the intersection between real boundary and free boundary, but these are different points that I haven't at all discussed. Okay, so I only cared about the free boundary itself in my discussion.
So thanks for the very nice talk. I have a question regarding these pathological examples. So once you prescribe the free boundary, how difficult is it to cook up a solution which attains this boundary?
Okay, so that's why I was cheating a bit. If you really want, okay, here there is always the PDE part of the theorem, right? So if you really want a Laplacian U equal characteristic of U positive in this way, then in fact this example doesn't exist. Because here implicitly there is a weight 1 in front that came from my gravitational force, which was constant of course. And then in fact you can put that into dimension, there is a very rigid structure. The reason why you can cook up this example is because in reality the obstacle problem is much richer than this. The obstacle problem, as people study it, will be something like this. You have an elastic wire, okay? Sorry, a metal wire. And then you have your obstacle, but let's say that my obstacle doesn't need to be a table. It could be some smooth infinity, maybe not analytic function that pass. So here is the wire around, and then this is my obstacle. Okay? And now you minimize the English energy again, if you want plus gravity, it doesn't matter. But with this as an obstacle. So this is my obstacle thing. And now I have my function u, but let me call it v here. That solves obstacle problem with a different obstacle phi. Okay? And then you can always reduce the problem back here. So there is a way always to go from this formulation to this formulation, which is to define u v minus v. So if you take the solution of the obstacle problem here and you subtract v, you get back to something non-negative, which will satisfy something like this. But the one here will change. The one here will be minus Laplacian U. Okay? So in reality, it makes sense because of this setting to consider a solution to the obstacle problem, which are something like, let's say, h characteristic of U positive, where h is strictly positive, but h may not be identically 1. And now, once you tell me that I have the freedom to choose h, then here to look up a solution which has this as a free boundary is not difficult because you do like a kind of Whitney type construction. So you prescribe all the derivatives and then you like extend a la Whitney in some sense. Whitney Cauchy-Poisson, an intermediate version. And you can easily build solution of this in the infinity class, not in the analytic class. So you can build up, there exists H infinity such that these are infinity curve and there is a solution of this problem. But you have to go to infinity.
Thank you also from me for that nice talk. In the context of the genericity, I wonder for the set of T, where the dimension of the singular set is like cogomate dimension 3, do you know anything beyond measurability? Like it's
Set of T?
Yeah, you say
it's
for
open.
Sorry?
It's open.
Open. Ah, that's very nice.
Yeah. So this is an open set. Yeah, the point is that. Oh, sorry. Wait. It's open here. Wait. It's open here. In dimension 4. Because once you know that the singular set is empty, having empty singular set is an open condition. In higher dimension, it's measurable. I'm not sure because so our theorem in some spirit looks a bit like when you prove SAT theorem, right? The set of critical values of function. How large is the right? You have a function from Rn to Rn, with some regularity CK, and depending on the relation between K, M, and M, you know something about the critical values, so the image of critical points. And usually the critical set doesn't have a super nice structure, but you can estimate the size. And this goes in this direction. So in this high dimensional set, I'm not sure what else we could say, but sorry, in dimension 4 and lower, it's open, which is, yeah, sorry, when I replayed open, I was like, doesn't make sense. It's open in the dimension, then something more else.
Yeah, so thank you for your talk. Yeah, when I was reading up about this problem, I saw that there are apparently a lot of applications to optimal control. So either maybe you can speak a little bit to that or provide a couple of references if you know.
Yeah, there are many applications. So essentially, this comes, yeah, I can find some references. I think there should be quite a lot. I have to check some survey papers. We wrote quite a few survey papers and some papers, especially when you use operators which are more general than Laplacian, there are a lot of references about stopping time. So there is always a probabilistic interpretation for the Laplacian. So solving a harmonic function, you can think of it like you fix a point, you run a Brownian motion, start from the point, you run it until it touches the boundary, and then you look which boundary data you get at each point of your Brownian motion, and then you just average over your Brownian motion. That's how you find harmonic functions. Now, in this case, there is the obstacle, right? Acting, the fact that your function touches the obstacle. So these solutions can be written as a stochastic control problem, where you have your random path that at some moment, you reach the quantized you stop. And the most classical interpretation that you can have for this kind of obstacle problem, for instance, comes from finance. So there are American options. So anyhow, we have options that give you the right to, buy or sell a stock depending on the underlying market price. And essentially, the moment you touch equals 0 is the moment where you want to buy or sell depending on which direction you're going. So, like there is a value, the obstacle acts as a fair price, and then as long as you are above, it's like, oh, I'm making money. But then the moment I touch, it means that I don't have any interest to play the game anymore and to invest. So there are all these stochastic control interpretation, for instance, of those problem. And this is also very well described in papers where people do also non-local operators. So you could do the same kind of problems, but you start to replace the Laplacian by some fractional Laplacian. And these are very natural in finance because then it means that the process is not necessarily just a Brownian motion, but there are also jump processes which describe the fact that markets can have discontinuities. And so, especially in the family of non-local obstacle problem, there are a lot also of discussions about the interpretation. So there is both the static problem, or there is the parabolic problem. You add a time derivative, and this is also very natural in all these control problems.
Are there any other questions? Maybe I allow myself to ask one question that I had. When you described all these blow-up processes, then I was wondering whether that helped to put into context this difference with the C11 and with the C infinity surface when you have to exclude points of codimension 2 with the fact that they codimension 3 only. Or could, whether this is like somehow related to understand a bit better the structure of the points that are bad.
It is related to that, but it's not this analysis. So this analysis has an advantage. So this is something that is explained also in another paper by Simon, Eric, and Georg. So they have one paper where they do the conjecture, another paper where they show some applications of this classification, which is useful. So the good thing of this theorem is that it applies both to regular and singular points. So it doesn't matter where you are, which gives you some information which is kind of uniform on the free boundary. So all the theorems studied today were very dichotomy type, in the sense you say something about regular points, you say something about singular points, but you say nothing about how they meet, how they touch each other. And if you want to treat that, you need the results of this form, because these theorem results allow this point can be in both sets. So they kind of treat the same regular point and singular point at the same time. what we did in our analysis, this convention 2 and 3, is really specific to the fact that you are at singular point. And at singular points you have extra tools that you don't have here. So this is too soft, I would say. This classification result is too weak to tell you anything about this co-dimension 2, co-dimension 3, because this classification is like doing a quadratic rescaling. You see, I'm rescaling over order 2, and I'm looking what I get in the limit. So this is a sort of C2 expansion of U around a point. I'm blowing up at order 2. This is like C2 regularity, because I'm doing quadratic rescaling. In order to understand this, you have to start to do cubic rescaling, fourth order rescaling, and so on. So you need to keep Taylor expanding your solution over and over at higher order, which is not trivial because this is not a smooth function. It's a function which a priori could have no Taylor expansion at most points. You try still to build it, despite the fact that a priori may not exist. So that's the
Okay, so if there are no other questions, then I think this regarding deserves a great applause for its nice